Hello everyone, so it's a great pleasure for me to be here and to give this short introduction and video. So I will talk to you about the eigenvalues of the critical orthogonal graph. This has been a joint work with Johannes Alt and Antinors, and we are all of us in the University of Geneva. So let's start with the model. So just considering the orthogonal graph. So I guess you all know already what is the orthogonal graph. So just choose n vertex, and between each vertex, draw an edges with probability p, and independently and randomly. So the mean degree of this graph will be kind of np. So this will be our main parameters, and it will depend on the number of the graph. Actually, we'll choose p going to 0 as n goes to infinity. So we consider the matrix, symmetric matrix of the adjacent symmetries of this graph. So it's just a random matrix, and with 0 and 1 entry, and we ask what can we say about its eigenvalue. Well, the first very classical result we know is the Semicircle Law. Well, as soon as the mean degree of this graph goes to infinity, we can get the Semicircle Law with the correct rescaling 1/square d. So as n goes to infinity, we have the Semicircle Law, which implies that almost all the eigenvalues are concentrated between -2, 2, or the outsider are just a little o of n. And there is at least one outside, which of order square root of d, which is created because the a is not centered. But so let's say for the following that a is centered by considering a minus e expectation of a. So except of this eigenvalue, are there any other eigenvalue away from the bulk? And so I have to mention the previous work of George, Bordenave, and North, which proves that something occurs around the regime log n. And also the work of Tico, Mironov, and Youssef, which work on the same subject at the same time as us. So here is the main picture that illustrate our results. So this is a spectrum. Here is the abscissa is the spectrum, and in the odd here is the parameter b when the degree is d is b log n. So well, I will keep the picture so you can follow here. So first, the thing -2, 2. No, sorry. Is just a semicircle law. So almost all the eigenvalues are here. And we know the density. Well, the density is 4 minus square root of divided by 2 power n. Well, we see here there is a sharp transitions around B star. So above B star, there is no outliers. I mean, all the eigenvalues are between -2, 2. And below B star, so B star is about 1/. So actually the spectral radius is larger than 2, and we know actually explicitly what this value is. Inside the blue part, well, you know that there is very few outliers, a little o of n, but actually it's a small power of n. So, sorry. No, if I just move, okay. So here we get a small power of n eigenvalue, And if I talk now about the eigenvector, in the red part, the eigenvector are completely localized. I mean that the eigenvectors somehow are equidistributed on all the vertices of the graph. And on the contrary, in the blue regions, the eigenvector concentrates on a much smaller set of vertices. So we can express it with, for normalized eigenvector, the absolute is almost optimal, square root of n, and on the contrary, the absolute infinite norm is bounded away from these things. And all this, okay, well, this picture actually can be extended quite far up to the regime d of square root of log n. So except for this power of n, the correspondence of the outliers are correct. Well, what occur about square root of log n? Well, actually this, okay, the localization result is not true in the middle of the spectrum because we can have some isolated vertices or small, very small graph which correspond to eigenvalue close to 0 but with eigenvector completely localized. And this band actually expand and breaks the picture at the regime d square root of log n. Well, so how can, okay, what create this beautiful picture? Well, sorry. Okay, sorry. Well, the main result is that there is a one-to-one correspondence between large degree and eigenvalue outside -2. So let's say if you look at the graph and if you see some vertex with degree twice as large as the mean degree of the graph, then it will create two eigenvalue away from the bulk, one positive and one negative. And actually it's explicit, so we know where these eigenvalues are. So if we have L large degree vertices, we will get L eigenvalue larger than 2 plus little o of 1, and L other eigenvalue larger than -2 plus little o of 1. With this, well, we know where there. Okay, so now I will just give you a few hints of so why large degree vertices lead to outliers. So just think of this vertex as large degree inside of the graph. So erase everything of the graph and just keep this isolated stars. Well, it's an extremely easy exercise to see that there are two eigenvalues for the graph of this star non-zero, which are square root of alpha and plus alpha. And so very closely we can think that for alpha larger than say 4 we will have outliers. But actually the truth, well, if you embed this star inside of the addition graph, the transition will occur at 2, and with these eigenvalues that appear. So a way to see is that this kind of star produce a BBP transition in the random matrix of the addition graph. Then why log n? Well, this is a regime where this kind of large degree, large star appear. So think of some large deviation result. So if you fix one vertex and you ask the question, does this degree can be larger of some alpha d? Well, the probability that it occurs is actually exponentially small. But because d is some log n, then it's a power of n small. Now, if you consider n such vertices, well, the number of vertex larger than alpha n will be given by some small power 1, some power of n. then this give actually can also get, okay, this gives the density actually of large degree, and this gives also the largest degree of the graph, and it directly translates with both the density of states in the blue region, so this power here actually leads to this blue region, the density, and these equations actually express the line here of the largest eigenvalue. Okay, so a few technical steps we have to consider. That we have to analyze extremely precisely the adjoint graph to get this estimate alpha over square root alpha, and we also have to prove that this eigenvalue actually has the only one in the spectrum. Well, this can be done with some moment methods on the non-backtracking matrix. And although, of course, we are to prove that the eigenvector inside of the bulk are delocalized, the buzzword is a local law with the green function. And in the last minute, I would just mention work what we are doing now and to improve the picture. So we try to improve some estimate inside the blue region, so that to prove that actually to have better bond on the localization thing here, and also trying to get the law of the fluctuation of this of the largest eigenvalue. So that's it. So I thank you a lot for your attentions, and well, question I guess is difficult, but you can send me a mail anytime. Thanks.